Right. Thanks, Philip. So I'll be talking about a generic way to model the class of effect systems where we care about program order. And in particular, to give an algebraic characterization to this class of systems that is specifically sufficient to actually model a range of prior work from the literature. The ultimate end goal of this, of course, being help guiding the design of new such systems, implementations, so you can build generic implementation frameworks, and communication, because we can have more targeted ways of describing and comparing these things. So during the talk today, I'll talk about a new such characterization and a way to derive a free notion of iterating one of these effects an arbitrary number of times. Also in the paper, there's some stuff I'll mention towards the end of the talk that comes back towards some of these design, implementation, and communication ends. So just to recap, since probably I've spent a little more time thinking about these things than much of the audience, effect systems are an extension to type systems. So they don't just describe the shape of data, but they also describe the internals of computation. So what happens as the computation progresses. So in general, we'll move from our traditional under assumptions gamma, ES type tau, to under assumptions gamma, ES type tau, and the computation has the following effects, chi, where these effects might have to do with locking, memory access, non-termination, or Java's checked exceptions, which is far and away the most widely used effect system. And for most effect systems, we have a nice, concise characterization, which is essentially a joint semilattice. Technically, there are things for effect masking you need a little bit more. But with just this simple model of joint semilattices, we actually get a lot. For example, we can do generic meta theory or implementations and think in a general way, what is the overall effect of running two expressions in sequence? So if E has effect chi, E prime has effect chi prime, then the effect of running them one after the other is just the least upper bound of both in a way that disregards the order. So for example, you can take this either in theory or in an implementation, provide a plugin for something like checked exceptions, and get out concrete derivations, like if maybe E throws an IO exception and E prime might throw an invalid argument exception, which I just realized is actually a runtime exception, then running the two in sequence could throw either of them without any regard to program order. Most effect systems fall into this bucket, which I'll call commutative effect systems to distinguish against the class I'm more interested in this talk. And so this is actually a surprisingly large space. You can get things like block structured lock ownership, checked exceptions, memory regions, capabilities, access to UIs, blocking your thread, and all sorts of other things. But the thing that they all have in common is that order doesn't matter for these systems. So these systems can't distinguish doing A before B versus B before A. And so we can ask the question, what happens, what do we get if we relax this restriction, if we let the effect system consider ordering? And this gets us stronger properties, more complex properties like unstructured locking, unstructured memory access, heap shape dependent locking, and even certain classes of trace properties. And so I'm going to call these sequential, following some terminology that Ross actually set up. And these systems lack an established algebraic characterization. So what do we need to capture these? Well, we'll still need a joint semilattice because we're still going to have some of the same uses that we would have in it traditionally. And of course, we'll need some kind of sequencing because that's exactly what the extension is for. And we're going to let that be partial. It might be the case that you want to allow A before B, but not B before A. So we want a way to indicate that. We'll need some way of iterating effects to handle imperative loops. And we'll need some nice equational theory for these things for simplifying complex effects. So if everything's concrete, you can, of course, just plug in the values for these operators and simplify. But if you have a polymorphic effect system with effect variables, we would like some algebraic identities we can use to simplify complex effects. So my proposal for this is called an effect quantale, which is a relaxation of a related structure called quantales. That's where the funny name comes from, and the paper has some references for that. But essentially, it's a set E of possible effects, a binary join, a sequence operator, which again is going to be partial. A top element, which is how we're going to mark partiality. We're going to interpret our top element as error. And a unit for sequencing, just one. Since we have these two operators, it's worth asking how do they interact, and they follow, you don't need to worry too much about that, but they're distributivity laws. Nothing too special. And then we require additionally that top is nilpotent, which together with the fact that it's top means if you have an error in one part of your program, you can't write these operators in such a way that you lose track of the error. It'll propagate up. And from this, we can get a lot of useful things, like we can derive a partial order as you would for a joint semilattice, and we can prove monotonicity of sequencing. And so this particular definition is not super complicated, but what's important is that this is actually enough to capture the existing structure in a lot of prior work. So for a concrete example, let's look at an effect system for atomicity. So Flanagan and Kadir wrote actually 2 papers on this. Most people remember their second one, which is a lot more powerful. But let's look at the simpler one, which actually fits in a talk. So the core idea there is based on Lipton's theory of reduction, which is a way to reason about roughly atomicity by considering how the local actions of one thread in a well-synchronized execution commute with actions of other threads. And so, for example, a lock acquisition in this top execution trace can commute to the right with some other thread's action without changing the semantics of the result because we know it's interference-free. And similarly, release moves left, while synchronized accesses can move in either direction. And you can pile together a bunch of right movers, both movers, and left movers together, and these you can always rewrite into an equivalent execution where these execute without interleaving. So it's effectively atomic. And in Flanagan and Kadir's system, each of these mover effects, mover types becomes an effect. So we have both left, right, atomic, and compound for things that are, nothing's wrong with them, they're just not atomic. So if we want to think about formalizing this as an effect quantile, we start out with their lattice and their sequencing operator. Top here is their top, which is really just compound. This is not an error. And they wrote their sequencing operator with a semicolon. And so if we want to turn that into an effect quantile, we can actually just basically add an error element, make sure it does the right thing in a join, and add the error element to the sequencing. And turns out they already proved the effect quantile laws just without the error element. So this already fits pretty directly into our framework, but sort of begs the question of, did we overfit, right? It almost looks too easy for that example. And these do cover more ground than just that one system. So in the paper, I give a derivation, a motivation for most of this structure in terms of just normalizing the judgment forms for a range of prior systems. And I've actually worked through trickier examples like doing unstructured locking with recursive acquisition, building product of effect quantiles, and while it's not in the paper, effect systems that actually track, for example, sets of execution trace fragments also give rise to this structure. We also have a clear relationship to what I'll call more foundational work in the sense that it's work focused on categorical semantics of these systems. The short version is that we end up with similar algebras. We're looking at the same problem, so they should be similar. And effect quantiles are more restrictive because instead of working from semantics backwards and focusing on what's necessary, this work is focused on capturing the structure that's already in a range of prior systems, and they actually have more structure than strictly you need to make sense. But then on top of this, we can also build a free notion of iterating one of these sequential effects an arbitrary number of times. And this is important because if we want to talk about while loops, we need something that expresses this. So this is usually written with this star operator here. And so if you want to type a while loop, the effect of the loop is the effect of the condition followed by 0 or more repetitions of the body followed by the condition again. And prior abstract work on sequential effects defers iteration. They were busy solving lots of other problems. But Mycroft et al. Note that if you just do the naive thing of just making sure you have a fixed point operator in the semantics, this has some unpleasant consequences. So in particular, it requires every effect in the system to be what's called idempotent, which basically means any number of repetitions of this effect back to back is equivalent to doing it once, which is too strong. Even this one example in the talk, Flanagan and Kadir's work, doesn't satisfy this. Most of the effects actually are idempotent, but if you repeat two atomic actions, this is no longer atomic. This is now compound. So we need something that's a little bit weaker than a general fixed point combinator, which we can induce from an effect quantale. So to do that, we need a little bit of lattice theory that's not sort of the go-to bits of fixed point theory for program semantics. And we're going to use what's called a closure operator, which is a function on a partially ordered set that is extensive. It'll only lift things in the partial order. It's idempotent, so if we apply the operator multiple times, that's equivalent to applying it once. And it's monotone, so it respects the partial order. And these have a couple interesting properties for our purposes, like the fact that the codomain, the set of possible outputs for these operator, is also exactly the set of fixed points, which is a consequence of this idempotent fact. Also interesting is that any closure operator, if it exists, is uniquely determined by its range. So if you give me a subset of this partially ordered set that you think these should be all the possible outputs from this operator, I can do a little check on that subset, and if it passes, I can give you back the operator, and there's only one. Another bonus for this is that also in the paper I work out 5 laws that any reasonable notion of iteration has to satisfy. 2 of them are automatically satisfied by any closure operator. So this is a good starting point. If we want to go the rest of the way, we can do a little perspective shift. Instead of thinking about exactly how iteration should work, we can think about what are the possible outcomes of iteration. And then if we can constrain that set, we can see if it gives rise to a closure operator. So the other 3 of those 5 properties impose a couple mild requirements on the range. They require that the range elements are idempotent. So they require that any result of iterating an effect, arbitrary number of repetitions is equivalent to 1. But they don't require this for every effect in the system. And then this range has to be closed under joins, and everything needs to be above the unit because we might not run the loop at all. So we need to be able to capture 0 iterations. And so if we do this, we end up with an operator that is essentially take any effect and we lift it to the least idempotent operator that's both greater than it and the unit. And you get something that satisfies all of the iteration laws that we lay out. Under a couple mild conditions that have to do with making sure there is a least such element and this closure under joins. And I'm calling them mild because every system I've looked at, when you look at the effect quantale, it passes these checks. So while in principle you can write an effect quantale that fails these properties for which you wouldn't get a useful iteration operator, I haven't found an example anyone cares about yet. These also have the benefit that the categorical semantics for these things are also well understood, so this hopefully should provide some leverage for doing this in the semantic world as well. The other question we have to ask about this, of course, is does this actually do what we want? Because here's one example of a closure operator that is well behaved and passes all those laws. Just return error. That passes all the laws, but obviously isn't what we want. So if we do this for a commutative effect system, if we take an effect quantale where we just reuse join for sequencing and throw away the ordering information, this turns into the identity. And if you use that to simplify rules that are written down for a sequential type system, we get back exactly what you'd expect for a commutative type effect system. If we apply this to Flanagan and Kadir's atomicity effect quantale, we get back exactly the same operator that they worked out by hand. So it's the identity everywhere except atomicity, and it takes atomic actions to compound actions. And if we do this for lock ownership, we end up with two cases. So if you iterate something that acquires or releases locks, well, we don't know how many times we're going to iterate this, and so that doesn't really make sense, and this operator correctly takes those to error and rejects those. And if we do it for something that has the same lock claims before and after, on those elements, iteration is just the identity, which is exactly what you'd expect. It corresponds to loop invariant lock ownership. Paper has a few more things, including an abstract core language with singleton effects and effect polymorphism, parameterized by an effect quantale primitives and a couple relationships between them. So we know these things are actually compatible with polymorphic effects, singleton effects. To make sure that I'm really capturing at least one system, we have an effect-preserving translation between Flanagan and Kadir's simpler atomicity checking calculus and an instantiation of our core language with the appropriate primitives. We also lay out precise formal relationships to prior semantic work and point out a bunch of subtleties related to substitution with singleton effects. Turns out you need one extra property when you start doing singleton effects to avoid collapsing everything. And that's actually it. Thank you.
Okay, are there any questions? Well, maybe I can start with a question. So is there something to be learned from this work for effect systems that are, for polymorphic effect systems that are not order sensitive, or?
Possibly. I haven't really gone back to think about how the connections made here apply back to commutative effect systems. But in general, the reason things break here is because under substitution, you might have things that are syntactically, statically, two different variables naming two different pieces of an effect, which under substitution become one and collapse, and you start sort of losing count. And in practice, that hasn't been a problem for a lot of commutative effect systems because often that same counting that needs to happen for, say, keeping track of how many lock claims you have is actually done by the runtime semantics with things like an in-sync block runtime expression. And I can't think of actually having seen one of those systems that only tracked that ownership statically. So there may be something, but I'm not 100%.
Oh, there's a question from Ross.
So this is very cool. What I'm curious if you happen to know, so assuming it's an effect quantile, did you happen to prove that like you are making the minimum assumptions necessary to express iteration? Or is there some additional structure you happen to know that you're relying on?
So I have not proved that I'm expressing the minimum necessary, but I've proved that I am satisfying these 5 properties, most of which are pretty natural for anything to make sense as iteration. They're things like running once counts as running arbitrary many times, running an arbitrary number of times plus 1 on either side is the same as arbitrary number of times. Nested loops unfold dynamically to some arbitrary number of repetitions. You can distribute over joins. And we have to include this case for if we don't run the loop at all, this still needs to work. So I don't, you could imagine throwing away this distributive law.
Yeah, that's the one,
but actually, and it would still be well behaved, you'd still get some reasonable things, although in practice, like compilers actually do optimizations that would make that unsound,
right.
If you didn't have that.
Cool, thanks.
here's another question.
So sequential effect systems seem like they're also related to ideas like session types, type state, some forms of linear type systems, where for the most part there hasn't been a lot of work on parametric polymorphism. Do you think that these ideas have applications or can be adapted into those settings?
So I don't know enough about session types to answer on that point. For type state, at least some of the systems where you express the change in type state, you could set that up as an effect quantile. The difference, though, is that in practice it seems like most of those systems require some kind of sort of dynamic reflection operator where you check what is the current type state this, and then do something else. And that is beyond what I've considered in this framework. So, and I don't know how that interacts with parametric polymorphism.
Okay, so I think we have to switch over. So let's thank Gordon again.